I'm going to talk about control integrity on IBM. My name is Varga-Perke. I'm shitposting on the internet under the handle Governor. I work at Silent Signal, which is basically a business company that we founded in 2009. And many of our clients are running these special systems called IBM Eyes, which were formerly known as AS400. Maybe I'm more familiar with that particular name. And we decided to focus on this platform in 2022. And here are some of our findings from the lower level of the spectrum. I have to mention that just like many of us, I'm also standing on the shoulders of giants. So, like Varga and Hugo did some excellent work in this area. What I plan to show you today are like the exact bits and bytes about how the low-level protection mechanisms on IBM look like. So, first a little introduction about this platform, because I guess most of you are not that familiar with this, as I wasn't a few years back. So IBM is so-called a mid-range platform. It was positioned above the so-called microcomputers in the 1980s. It was released in 1988, but it's not like a real mainframe, but still it has some really neat high reliability and backwards compatibility features. It's also a vertically integrated platform in the sense that IBM produces these machines from the lowest level hardware, including the CPU, to the high-level operating system, and most of the applications that come with the platform, of course, as a third-party developer, you're free to do your own stuff. They run power CPUs, which are basically power PCs, which with some vendor-specific extensions. We will talk about those mainly. And it's a really revolutionary operating system. It works really differently than like Linux or Windows. We'll see why. It's an object-oriented operating system. It also has a unique subsystem called base, but we won't talk about this. I will talk about what we usually call the native ABI stuff. So how should you imagine this object-oriented operating system? On a usual operating system, you have files, you have processes, you have databases. On IBM, all these concepts are abstracted away and say that everything is just an object that live inside a single-level store, or the SLS, which is a singular address space for both disk and memory. Which, if you think about it, is a really interesting concept. So you don't have a file system, you just have this huge virtual address space, and you put everything in there, and the operating system basically handles all the caching and persistent stuff for you, basically transparently. So inside a single level store, you have 64-bit addresses. The first 40 bits is the called segment identifier, and the other 24 bits that remains will point to an offset inside the particular segment. Yeah, so this is true for security level 40. Security levels are like global configuration variables that define some basic security properties for the system. For example, security level 10, you don't even need to have a password to log in. So that's not great, obviously. So most of the users these days use security level 40, which will provide all the standard features like separating the processes of the user data of the distinct users, requiring password, etc. And you have security level 40, which is a bit stronger. I will now talk about security level 40 in this presentation. So to give you an example about the object-oriented operating system side of things, my favorite example is about how processes or program objects work in this system. In IBM, the executing thing is conceptually the same as the store thing, and this is like really special. You just have a piece of code inside a single level storage. It has an address, and whether you want to edit it, or whether you want to run it, you actually will work with this particular address inside the SLS. But just like when you were programming Java or using any object-oriented language, the whole data, so the actual RISC code that runs on your system is encapsulated in the terms that normally, as a standard user, you're not allowed to flip around bits and bytes inside the machine code. You just have a public interface that allows you to execute the program. So, how do we develop software on this system? Here's where the so-called machine interface comes in the picture. In the simplest terms, the machine interface is like an architecture-independent bytecode, an object-oriented bytecode, and if you use any high-level language like C or RPG or COBOL, which are the most common ones on IBM, your system will first compile this high-level language into the machine interface, so-called bytecode. And from this bytecode, the operating system can emit native code that can be actually executed on the system, similar to like JIT. But the thing is you as a programmer don't have to know about what the underlying architecture is. And in fact, AS400 had a CISC version back in the day. Now it's a mixed RISC. But as a programmer, you're not concerned with that because your software will run without modification across different generations. But let's talk about security, okay? AS400 is surrounded by a bunch of myths. I collected some of those, like IBM itself can be contaminated by viruses. The only operating system that has never been infected with virus, Trojan horse, or malware. The architecture of IBM system makes it highly unlikely, that's more careful wording, that a virus could be written to attack it. And while these are definitely like statements on the internet, you can find them, we can also see that experts are warning against misuse of the external interfaces, like you can have web applications running on IBM, you can have a shared file system exposed by IBM, and these can facilitate attacks just like everyone else. But I was really curious about this virus thing that they're talking about. Also, a colleague of mine took some really serious research on the application side of things and uncovered, of course, a bunch of CVEs. We talked about this on Troopers a couple of days ago, so I won't go into details of that. I'm mostly interested in memory corrections, like how do they work? We can program in C, what can go wrong? So let's take a look at a really simple spatial safety violation. Here's a test program I wrote. Of course, it takes in a number and a character buffer content from the user, and then it explicitly just does an out-of-bounds read. And also there are now bounds checks about how much characters the user would put into that particular buffer. And sure enough, this is what we get. So maybe it's not obvious because IBM uses FCDIC, but these C1, C2, C3, C4, C5 are like A, B, C, D, E, like characters. So we could obviously insert more than 4 characters inside the buffer. We could leak the contents before and after the character buffer. Those 40s are like white spaces. These 13 and 37 are the numbers that also the number I put in. But when I printed the number in hexadecimal, we could see the C5 character also corrupted the integer that was stored in memory. So memory corruption is definitely possible. And what's worse, since we have this single address space for everything, if we have a memory corruption, we basically have a privilege escalation locally, because we can just go into a completely different program, a completely different user, and start to play with the addresses there, and that's not good. So even if we can write a correctly challenge where we could artificially introduce vulnerabilities and exploit them to manipulate machine code directly, we basically won. And of course, if you look for these error codes on the internet, you will find a bunch of forum posts. And these error codes are indicating memory corruption issues, so these problems do occur in legitimate applications too all the time. So let's reverse engineer stuff, see how things work, see how we can write an exploit. I already told you about the machine interface. This is just a more precise description, so I'm just skipping this. The first problem that we'll face when we try to reverse engineer the program objects on IBM, this is the object type that we are mostly interested about, of course, is that, as I said, programs are not stored as files or continuous bit streams. So how do we extract them from the system in the first place for analysis? The good news is that the platform gives the opportunity to move around objects, for example, between different systems, over a network, or on tape, or whatever. And this mechanism is based on so-called save files, which is a universal serialization format. So we can take a program object, and we can create a file object from it, and then we can download it via FTP, for example. So that was easy. Save files has an undocumented format, but there is this free but closed source reader called JSLF, which can be used to extract the contents. And when we extract the contents of a save file, we get a bunch of serialized objects, because a save file can contain multiple objects. So we can get our PGMs in some serialized form, but unfortunately that's undocumented. So let's write a parser. How do we do that? Well, fortunately, for low-level debugging, IBM provides the system service tools, which is a special program inside IBM that you can access only with the highest privileges, the Q security officer, which is basically the root. And it allows us to have some insight about what's going on in the system, but as you can see, it has its limitations. You cannot use breakpoints, you cannot trace execution. When you look at register dumps, some registers are explicitly hidden from you. So I just won't show you what's in R2, for example. Here's a small video of how it looks. So we log into the system. This is the standard so-called pre-screen interface of IBM. And to access the system service tools, we have to, again, provide a password because it's so sensitive. And we can traverse the menu until we can, for example, start listing processes. And here we find the multiple processes running currently in the system. We choose one of them. And these are the three main things that can be done with the processes, a bunch of internal structural information, and this is exactly what we will use. And this is the memory dump of the process. You can see those T's all around. Please remember that episode. And here's another view where you just get a hex dump from the single level storage. So it's just a memory dump. But for example, you cannot easily stop the program to give you a view of the memory at a very precise moment. So I usually just use scanf to make the program wait and to debug stuff. So I'm not really sure what's happening right now with the projection, but okay, here we go. So when I downloaded some of these files and looked at SST, I quickly realized that there are like matching patterns on what the SST is providing me and what's inside the file. So I just go on and wrote up about 1,300 lines of Kaitai struct. I really like this tool. It's really easy to develop the parsers with it. It's really easy to debug your parsers to see what's going on, for example, by generating a Python parser and use it in a repo. So you can immediately see what works and what's not. And when everything is done, I have this favorite trick of just producing a Java class from this Kaitai description, and I can just use it with Ghidra. So now with this little trick, we can immediately have a Ghidra loader from a Kaitai struct. We did this with Xcov, which is AIX's executable format. But this is how it looks like mostly for AS400 BGMs. Here we just initialize a byte stream, so from one end to the other, initialize the generated class with this stream, and after that we can just access all the different segments, for example, that's stored inside the serialized program file, as if this was a proper Java object, because it is. When we visualize all this and when we debug all our mistakes, we can load this up, for example, in the Varga IDE, and here we can see that this save file will have a member that's called risk code. So this is like the machine code that we are mostly interested in. When we load this up into Ghidra, as you can see, we can also extract the load addresses where we should put all our code in. Now we can see that Ghidra can successfully decompile some PowerPC instructions on the above, but here at 7C, it just fails. This is because IBM, of course, implemented its own proprietary extensions to the ICA. This is called the Power AS architecture, so we have some instructions that we don't have on any other PowerPC processor. Now, it will be tricky to figure out what these bytes do, but fortunately, we still have access to an AS400 system, and it has a built-in decompiler. So, for example, we can see that this fading code that was shown before is basically a stored one-word instruction, so we can type this whole thing up and create like an extended PowerPC processor module for Ghidra. I did work on this for a long time, and then little bird told me that IBM's an old version of their internal documentation is on the internet somewhere. So I could really refine my work and verify stuff. So now we have a pretty complete loader for Ghidra and an improved processor module for big endian PowerPC, and we can basically decompile everything. We even have some symbols and whatnot. This will be also shared after the presentation. Now that we have the processor module, Ghidra can also help us to decompile code. As you can see, this decompilation output is not beautiful yet, but we are getting somewhere at least. So some findings about this is that I can figure out the register usage, the calling convention that's implemented inside program objects. Of course, since we are talking RISC, it has much of registers, so whenever they can, they use the registers for parameter passing, for example, but pointers are always passed on a stack, but they have different stacks for different stuff. For example, when you call a function, there is a stack pointer that points to the arguments, another stack pointer that points to the local variables. and return addresses live at a completely different segment. We'll see why. I couldn't really handle this double stack thing in Ghidra, and I have this question open at NSA's GitHub repo, but if someone has had experience about how to solve this, please talk to me. So now that we could extract all the relevant information from these serialized program files, let's see how we can actually write those exploits, how we can attack the system. If you looked carefully, you saw this funny little instruction called set tag inside this assembly that I just showed you. It's there because the Power AS extensions implement memory tagging, but it's a really different kind of memory tagging that you see on ARM, for example. This kind of tag is just single bit, so it's no really cryptographic magic behind, and you cannot really leak this value and cannot really overwrite this value because it's not living inside your memory, so to say. I'm not sure about the implementation details, but they say that it is somehow encoded in the error correction code of the RAM. Little bit of magic, right? So how we use this, here's a small example. So we just issued set an instruction, it's a standard instruction, it's unprivileged. And then the next store instruction will mark the stored keyword, which is 128 bits, as tagged. And these were these T markings in the memory dump, if you remember. And after that, and this is the interesting part, if you want to load that keyword with LQ, the load instruction sets some bits in the exception register, and the TXER instruction, like trap on the XER register, which is the exception register, will trap your program if those bits were not set properly or as expected. So the basic question, the basic information that we're trying to store with this single bit is that somewhat along the lines that was this pointer created in an approved way. An approved way means that something that the compiler expected and accepted. So the consequence of this is that if I try to corrupt a pointer, it will break this tag to break this one extra bit, and on the load, the program will trap and will not dereference the corrupted pointer anymore. So I think that's pretty neat, and it kills much of the standard exploitation strategies. But of course, we can be smarter than that, right? So like with idea 0, let's just write some shell code and jump to it. So as I said, we have this 128 bits long pointer thingy. These are so-called typed pointers or thick pointers. Here's an example with some deck heresy. If you look closely at the printf function call, we have 3 format specifiers, but just 2 variables. This is because this is the way I found how to leak out the tag and the address of any particular pointer. The first 64 bits has this first byte set to 80, which kind of means I'm a data pointer, and the rest of it, like the next 64 bits, are just the SLS address. So who goes right about the PowerPC AS tag memory extension mentions that LQ doesn't only check the tags that we just talked about, but it also can check the types. So the code word that it loads, it will contain some type information, and the expected type is somehow encoded into those last 4 reserved bits that you can see in the end of this piece from the official documentation. So this is how, for example, a function pointer call looks like on IBM. Here we have the load quad that we will load in a pointer from the stack, pointed to by R41, and it will be stored in R8 and R9. And here we have the extra undocumented part also decoded in Vidra. And here on TXR, here we have this OXA mask, which corresponds to the expected time. Then we have some pointer references, not that important, and finally we do a branch based on the pointer data that we extracted. So what I did was to create a small script now that I had everything in Vidra, and did just some little statistics about how LQ instruction followed by a TXR instruction are connected together with the corresponding masks. And fortunately, what I found was that the LQ mask and the TXR masks are really consistent. So they really confirm that they are really related to each other. So for example, when the LQ mask is 1, the TXR mask is A. So when we try to load something that the type for which is 1, then the TXR is checked at the position 8. And this is the final table I could create. So for example, when we are trying to resolve a data pointer, then we have the 80 type byte that we saw a few slides back. This will be loaded with an LQ mask of F, and the success of the type check will be then resolved or verified with the TXR with mask 3. So as a consequence, we can't transfer control to that data via pointers because this type check will fail with the LQ TXR pair of instructions. But we saw at the very beginning that simple out-of-bounds access is still possible, so why don't we just use a large enough overflow to go to other sections, to go to other users' data. Here's a little piece of C code. I'm accessing if position of the buffer str, and this is the corresponding PowerPC assembly. Here another load instruction called LTPTR, load that pointer, is used. And here you can see the add instruction that is used to shift the pointer with the appropriate offset to an out-of-bounds position, hopefully. What we have here is this sneaky little instructions TD, which is a trap double word. It has 3 arguments, R7, R8 in this example, and some constant value. If we look at the official documentation, so this is the publicly documented instruction, then we see something like this. So trap developer can compare the values of LA and RB registers based on some criteria, and this criteria is encoded in the TO part. But if we look at the actual mask that we just saw in this assembly, this TO mask doesn't make sense because it should always trap. So either 2 values are less than, greater than, or equal to each other, but we are trapping at all 3 cases. So either there is a trap handler that does some magic, or there is some undocumented behavior for this instruction. Again, I did some statistics based on the disassembled data, and I found that even in standard system programs, these kinds of TD masks are the rule and not the exception. So this means that if we try to handle these cases with a trap handler, it will probably have some really serious performance penalties. So based on this, we can say that this is probably some undocumented behavior corresponding to the TD instruction, which basically checks if the top 40 bits of the original pointer and the pointer moved around with the offset match, so that we don't move out of our segment. This is the right moment, I think, to mention that the C compiler on IBM doesn't really implement proper C, but a subset of it. So, for example, you obviously cannot do a JIT compiler with restrictions like this, right? Because it will break the main security model of the system. So here I brought a small video. I wrote a small program, and what you will see here is not an exploit, because I'm cheating. I'm cheating because I will patch out this sneaky TD instruction out of the program and see what happens. So this is my program running on IBM. And this is another window by the security officer who can do anything on the system. And with this security officer account, and here's the cheating part, I just patch out the threat double word instruction. My program just helps me with showing the correct pieces of memory to change. Here we found the address that needs to be patched. So we go back to SST that we saw before. And this is the trap double word instruction. We'll just knock it out. Fortunately, risk is every instruction is the same length, so you don't want to worry about messing things up. Now we re-execute our tricky program, and you see, while executing the program, we are also modifying the stored program. So now the patched program is executing, and now just grab some addresses from some privileged process and try to increment our pointer so that it will point to outside of our segment to the security officer processes. We'll once again use this one. Here the point is to just find. Here you can see the general purpose register is masked out because even the security officer is not allowed to see what's in them, which is, I think, interesting. But now we have found a proper address with some interesting data, namely instructions from another process which don't belong to us. And we could successfully dump the memory contents. Of course, maybe this is a program that we could also use and also could execute, so maybe this is some public information. So let's see if we can dump some stack or heap data. There's this E65, blah, blah, blah. And this was also successful. So this data belongs to the security officer, and we are running our debug program as a simple user. So this clearly now violates the security assumptions, but as I said, this was cheating. can we do better? We can just move pointers outside their original segment, but we just could verify that this is indeed a single instruction that prevents us from doing that. Can we just return, overwrite return addresses? As I said, return addresses are stored at a completely different segment, so because of the previous hardening or previous mitigation, we cannot just corrupt anything there, because to those segments only the register R1 or maybe R2 is pointing, and these two registers are reserved for like system stuff, and they are never used when emitting risk for user code. So that doesn't really work. My next idea was, well, after reading about a bit on data-only attacks, is to use a so-called out-of-context call. Here is my little crack me, but as I said, crack me can be good enough. Here I have an array of function pointers with two very innocuous calls to the lower and upper function that converts things to lowercase and uppercase. And I happen to have a pointer to the system function, also with some constant parameter. But since I can freely over or under index the function pointer array, I will hopefully be able to reuse this pointer that's already on my segment, right? So here we could verify the program works as expected. But if we provide -1 as the array index, and we provide an IBM command as the parameter, the program executes this other function and not what it was supposed to do, which is great. This is basically an exploit for IBM, but it's, let's be honest, it's pretty useless, right? We still cannot run risk code. This is just a theoretical possibility. If you find a memory corruption on the other side of the security boundary, and if that corruption happens to be on a segment that has some useful function pointers, for example, then this may be useful, but since segments are pretty small, I don't see too much chance for it, to be honest. Here are some of my fails or things that didn't work at all. I was experimenting with misaligned loads, then type confusion, and time of use. The main problem with this area is how to get some useful pointers in the first place. Like, how would I construct a new pointer to the system function, for example, with the constraints I just showed you. So these weren't really successful, but there is an addition to that. What I didn't look at were like translator bugs, so bugs in the compiler basically. I didn't look into microarchitecture. IBM definitely puts out advisories about microarchitectural, like speculative execution attacks affecting their power CPUs. So that's definitely a possibility. But since I cannot just easily play around with risk code to manipulate state at the lowest level, I haven't put in the time for that. But maybe for future research this can be interesting. But for temporal safety, I talked to a bunch of smart people at Troopers, and when I talked about them about this very topic, I realized that even though I read that IBM isn't really supposed to allocate the same address again and again, because it could lead to this user-to-free kind of situations, I never really tested it. So yesterday I wrote this little program that basically just allocates a bunch of memory, fills it up with 41, 41, 41, and then just periodically checks, frees everything, and then just periodically checks if there are any other bytes in the previously allocated space which are not 41s, 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 meaning that someone else did something with that piece of memory. And this is some of the data I got from it. It doesn't really matter what it shows. You just saw that they are not 41s, definitely, right? But since we already had the pointers in our program, we could still dereference these pointers and still dereference data that weren't put there by us. It's suspicious that this dump contains some repeating patterns, but I'm not sure yet what these are, so maybe this can lead to something. But as I said, I just found this yesterday, so if you have ideas, any other ideas based on what you just saw, probably there are many people who are better exploiters than I am. So please talk to me, because it would be really nice to have some fundamental breakthrough here. And this was basically the gist of my presentation. Here's just a small summary. So memory corruption is definitely possible in IBM, but this control flow integrity stuff makes exploitation quite hard. And although I managed to put together this very convoluted exploitation scenario, as I said, in real life, I see a very low chance that this will lead to some good results. On the other hand, logical bugs, as I said in the beginning of the presentation, are really appealing, and we have like hundreds of them right now for MPs, for example. What I haven't talked about is that if you think about it, with the serialization to move around objects between systems, corrupting the serialized form of the objects to contain different pieces of risk code, for example, patching out these safeguards that we talked about, is like a really obvious value and really the Achilles heel of this platform. What IBM does about this is that they include like cryptographic checksums into the safe files, and we don't know how those are produced, but theoretically they should be the same on all systems. So if we would be able to extract the algorithm, we would be able to construct valid-looking safe files that contain risk code without safety checks, and we have universal privilege escalation. This has actually been done by Les Swagart before for version 5 of IBM, but since then these CRCs got much more convoluted. But now we have some tools to do the reversing and find those algorithms finally. Unfortunately, I'm not there yet. If you want to try out this system, there is this great site called pub400.com that gives you access to these systems for free, basically, and you can even buy custom IBM Power-based hardware from Raptor systems. And if you want to dig into details, I have this whole thing that I told about in the write-up form. You can now read on the internet. I just published the Gitra extension, and here are the guideline definitions for parsing saved program object files. They are not like production quality yet. They work on my machine mostly, but I'm accepting all requests and issues. So thank you very much for your attention, and I think we should do questions outside because we are delayed a lot. So thank you.